Hello everyone, I am Hassan Nagatu from the Korea Institute of Science and Technology. In this presentation, I'm going to talk about our work and approach of formulating a homogeneous Jacobian for parallel manipulators with mixed DoF. The Jacobian matrix, which is defined as a linear map between the actuator rate and the velocity twist on the operational space, plays an important role in the determination of workspace kinematic performance evaluation, optimization of geometric parameters, or singularity detection. The general inverse rate kinematic equation of the parallel manipulator can be described like this. While Q dot is the actuator rate in the joint space, G is the inverse Jacobian, X dot is the constraint compatible velocity in the operational space. The most used algebraic characteristic of Jacobian to quantify and analyze manipulators' behavior are condition number, minimum singular value, or manipulability. However, these indexes are scale and unit dependent, and we cannot directly use them for manipulators having mixed DoF, which is a combination of linear and rotational motion in the operational space. Therefore, researchers tried to solve this problem by introducing two broadly categorized approaches. The first one is characteristic length, and the second one is point-based method. In the approach of characteristic length, the Jacobian is normalized by dividing the natural or characteristic length out of the translational elements. However, to derive L is not consistent and cannot be uniquely determined. Moreover, the geometric interpretation of the characteristic length is very unclear. The second approach is point-based approach. In this approach, number of pointers on the moving plate are selected and mapped to the joint rate. The mapping matrix is achieved by taking the partial derivative of the joint value to those selected points on the moving plate. Moreover, by taking the partial derivative of independent terms of these points on the moving plate with respect to the dependent terms, another matrix that relates independent and dependent ones are established. By taking the multiple of these two Jacobian matrices, a 3 by 3 dimensionally homogeneous square Jacobian is achieved. This Jacobian is dimensionally homogeneous, so it can be used for optimization, workspace determination, or other purposes. However, as it can be seen from these equations, it involves very tedious partial differentiation procedures, which makes it very difficult to derive and understand. In order to overcome this, we proposed two approaches of deriving dimensionally homogeneous Jacobian. The first approach involves 3 steps, and the first step in this approach is establishing the relationship between a constraint-compatible moving plate velocity and the linear velocity of the selected points on the moving plate. Then we derive the relationship between the constraint-compatible task velocity and actuated joint velocity. At this step, we use a closed-form analytic forward rate kinematic relation from reference 11. Finally, we establish the relationship between the selected independent point, linear velocity of the moving plane, and the actuated joint velocity. Assuming that the manipulator has this kind of moving plate, the relationship between the moving plate velocity and the branch velocity can be described like this. By rewriting this equation in matrix form, we establish this simple relation, where VB is the linear velocity, JBP is the mapping matrix, and X dot is the velocity of the center of the moving plate. Since only few points are independent and are sufficient to describe the motion of the moving plate, the selection matrix is used to extract the independent terms. Then by left multiplying this matrix with the selection matrix, we obtain a 3 by 6 matrix that maps the moving plate velocity 3 independent points. The second step is establishing the forward rate kinematic relation that maps the X dot to the Q dot A. So here we have the constraint compatible task velocity, and in the right hand, so we have the velocity of the actuated joint. while W and Y are given like this, which are made from the elements of the inverse Jacobian. Finally, we substitute x dot into the branch velocity to map the independent velocity of the selected point on the moving plate to the actuated joint velocity. This mapping matrix has a dimension of 3 by 3 and is dimensionally homogeneous, which can be used for analyzing the workspace, measuring the manipulator's performance or optimization. To verify the validity of the approach, the 3PRS parallel manipulator in reference 10 and 12 is simulated, and its workspace is determined using the condition number of GH as a maximum threshold to keep it away from the singularity. Talking about the workspace, there are two types of workspace in this paper, and their definition is as follows. One is reachable workspace and the other is dexterous workspace. Reachable workspace is a set of all possible end-effector poses attainable without having transit and non-singular configuration. This can be defined by the maximum reach of the manipulator caused by the joint limit. While the dexterous workspace is a subset of the reachable workspace, includes all poses of the end-effector attainable while maintaining some minimum level of dexterity defined numerically by the maximum permissible condition number. For the 3PRS manipulator, giving the link length and radius of the moving plate as 1 and setting this condition number as a threshold, we obtain this workspace, which is same to the result of reference 10. The second method is based on the limb level Jacobian. So by driving the limb level Jacobian and using a reciprocal scale relationship, we obtain the limb constraint and limb actuation Jacobian. And then we establish the inverse relation that relates the terminal linear velocity to the actuated joint velocity. Then we found this relation. Here we have the active joint and constraint. Here we have constraint Jacobian and active joint Jacobian related that the linear velocity of the terminal. Since we are looking for the independent relationship between Vi and Q1.I, the above relation is inverted via the optimization. So solving this problem is transformed to the optimization problem as can be shown here. And when we solve this problem, we obtain the velocity of the branch is mapped to the actuated joint velocity via this matrix. Writing this equation 3 times for the 3 legs, we obtain this relationship. And then by combining them and rewriting them in matrix form, we obtain this relation. The velocity of the branch has dimension of 9 by 1, and the mapping matrix has 9 by 3 dimension, and the actuated joint velocity is 3 by 1. However, only 3 independent terms are sufficient to describe the motion of the moving plate. So only Z components are selected using the selection matrix. By pre-multiplying this matrix with the selection matrix, we obtain a 3 by 3 Jacobian matrix that relates the actuated joint velocity to the 3 independent linear velocity of the moving plate. By applying the same manipulator on this Jacobian with the same geometric parameters, we obtain the following workspace. It is identified as a reachable workspace in reference state. Our result obtained through this procedure is the same to the result in the reference state. From the result, it is observed that the condition number of the Jacobian is obtained via the first method determines the dexterous workspace. However, the second method detects the reachable workspace. Both approaches are entirely dependent on the existing analytic Jacobian information, and thus are derived in the analytic procedure. The approach entirely removed the complicated partial differentiation procedure that existed in previous works. Both results can be used to determine the manipulator's workspace, to optimize geometric parameters, analyze the performance, or detect singular configurations. Thank you.